Dear students, in this module you will learn about reactivity of transition metal complexes. After completion of this module, you should be able to know about the basic principle of chemical reactivity. You should also be able to understand different type of chemical reactions that transition metal complex may undergo, and you can answer the question why there is need of exploration of new principle of chemical reactivity even if we have an existing model of ionic and covalent bonds. So let's introduce the topic. Every system wants to be independent and self-sufficient. That is the main reason behind reactions of atoms and molecules. For example, atoms, they may be same or different, atoms combine to complete its valence shell and form molecules either by electron transfer or through electron sharing. But bonds that hold the atoms too have limitations, and after reaching a certain energy level they may break. After breaking the old bond, new bond either of previous composition or of new composition may form. Principle of chemical reactivity is regulated by certain thermodynamic principle, but the basic remains same, that molecule wants its independent and self-sufficient existence. The satisfaction limit of atoms and molecules are very high, and therefore every atom and or molecule may react to frame new molecules. This is how billions of billions molecules have formed through a limited number of elements, and no one can say exactly about this number. When we talk about the transition metal complexes, our imagination tells us about a comparatively bulkier molecule with extremely high overall entropy. When I talk about the overall entropy, I mean to say the entropy that system has and that surrounding occupy. So for the bulkier molecule, bulkier transition molecules, we expect to have higher overall entropy. Therefore, we expect that system should be independent and have self-sufficient existence. So, as far as chemical reactivity is concerned, such system should be inert, but this is not the actual case. An extremely stable molecule like cytochrome may undergo electron transfer reaction. This is how message transfer occurs in our body. Similarly, hemoglobin may undergo oxygen association and oxygen dissociation process. Oxygenated hemoglobin may also undergo ligand substitution reaction with CO2. Examples can be even more. But our emphasis here is whether we can chalk out principle of chemical reactivity for such systems. And on the basis of such principle, are we able to predict a reaction before it proceeds in nature or in laboratory? That's how chemical principle can help chemists and ultimately to the society. Let's discuss different kind of reaction one by one and chalk out about the driving forces and the principle of chemical reactivity behind the reaction. So let's discuss first associative reaction. We also call this reaction as addition reaction. Reactions in which ligands are added to a metal complex or metal ion without removal of any species from the substrate is called associative or addition reaction. For example, two molecules of water can get associated with tetraamine manganese second complex to form an octahedral geometry. Schematically, you can see here in the equation, if several L-ligands is adding upon MLN ligand, you can get a complex MLN L-M. So when tetraamine manganese second complex will when react with water molecule, then a new complex MnNH3 whole 4 H2O whole 2 will form. In a special case of addition reaction, attacking species can increase both coordination number and oxidation number by 2 units. And the kind of reaction is called oxidative addition reaction, because in this case both oxidation and addition processes has gone simultaneously. For example, a hydrogen molecule can get added as 2 hydride ligands to the Wilkinson catalyst. This type of reaction is called oxidative addition reaction. Apart from other thermodynamic and kinetic consideration, a common sense that suggests cause of addition or oxidative addition reaction is their desire to fulfill 18 electron system in the valence shell of metal atom or ion to attain nearest inert gas configuration. This is one among the several driving forces for the completion of such reaction. Now let's learn about the second type of reaction called elimination reaction. It is reverse of addition reaction, and in this procedure ligands break from the metal complex to produce more stable complex. Elimination reaction can be divided into 3 parts, and they are dissociation, abstraction and reductive elimination. In dissociation reaction, a ligand breaks from the system to provide a less strained product or intermediate. For example, in the process of hydroformylation of alkene by the catalyst HCOCO4, CO group first breaks from the catalyst to generate a vacant site from where a catalytic cycle starts. Here, schematic reaction diagram is shown. You can see from HCOCO4, CO group is broken away, because of which a catalyst, main catalyst HCOCO3 generates. This is the example of a dissociative mechanism. In case of abstraction, coordination number of metal complex doesn't change. You had seen earlier, when CO group was removed from HCOCO4, coordination number of cobalt was decreased by 1 number. But in case of abstraction, coordination number of the metal complex should not change. Only removal of a substituent from a particular ligand takes place, and this too is generally used to be done by some external agent. The main reason for abstraction is for minimizing steric strain in the system and sometimes generation of an intermediate which can produce more stable product after further reaction. 2 kinds of abstraction, that is alpha and beta abstraction, is reported in literature. The representative diagram for the same is given. In case of alpha abstraction, as you see in the diagram, methoxy group is moving away or removed from the system, and in this system methoxy group is attached onto the carbon which is alpha to the metal atom. By doing this, you can see the coordination number of metal have not changed. Earlier the coordination number of metal was 4, and even after removal of the methoxy group, the coordination number is still 4. So removal of OCH3 group, that is methoxy group, from alpha position didn't change in the coordination number of the metal atom or ion. While in case of beta abstraction, generally not from hydrogen is abstracted not from the carbon just attached with the metal, but it used to be removed from the carbon which is attached from the first carbon. That is, the hydrogen will be abstracted from the beta position of the carbon, and therefore you can see by doing this a new product used to form, and in this product we can have coordination number of metal still 4. So coordination number has not changed. In this case, hydrogen or a group was removed from the beta position of the metal atom or ion. Deductive elimination involves a process by which both coordination number and oxidation number of the central metal atom or ion decreases by 2 units. For example, in the same case of hydroformylation reaction by the catalyst HCO-CO4, which we have cited above, the first step of the catalytic cycle involves reductive elimination, from where an 18 electron system converts to 16 electron system, and removal of 2 ligands regenerate the catalytic cycle. So you can see here in the equation, in this case you can see when an aldehyde removes from the system, it regenerates a 16 electron system from 18 electron system, and therefore reduction takes place from 18 electron system to 16 electron system. Also in this case you can see 2 groups, that is one is hydride group and other is the carbonyl group, breaks from the cobalt, and therefore coordination number is decreased by 2 units. So it was the case where both coordination number and oxidation number was decreased by 2, and therefore this process was called reductive elimination reaction. Steric strain is one of the main reasons for the reductive elimination process, because by this process generally 2 ligands removed from the system, which make the system sterically relaxed. Now let's go towards the insertion reaction process. In insertion reaction, an already attached ligand to metal get inserted between a metal and ligand bond. Among the several such processes, hydride insertion, methyl insertion, carbonyl insertion, etc. are reported. By the insertion reaction, system minimizes steric strain and opens a vacant site on which further reaction can proceed. An example of the insertion reaction. You can see in this example, an hydride ion or hydride group removes from cobalt and attacks onto the beta position of ethylene group attached from the cobalt by forming a pi bond. So hydride moves from cobalt to convert a pi complex to a sigma complex. In this process you can see the coordination number of the complex was decreased by 1, and by this process system has been relaxed, and one more space was generated on cobalt on which a further reaction can proceed. Now let's learn about the electron transfer reaction. An electron transfer reaction involves transfer of electron from one metal to other. 2 cases of electron transfer reaction have observed. In first case, 2 metals are the part of same coordination sphere and electron is transferred from one metal to other via bridging ligand. This type of electron transfer reaction is called inner sphere reaction. In the representative example, electron gets transferred from M' to M via a bridging ligand X that you can see in the example given here. In such processes, electron pass by making ligand tunnel to decrease the potential barrier of such kind of transfer. Now let's move towards the second type of electron transfer reaction, in which two metals might be the part of different coordination sphere and no species bridges the electron transfer process. This type of reaction is called outer sphere mechanism. For example, in our case, an Ml6 complex when reacts with Ml-6 complex, in first case if A plus was the oxidation state of metal and B plus was the oxidation state of M dash, then after the electron transfer process from M dash to M, the product that formed was Ma plus 1 L6 and Mb minus 1 M dash B minus 1 L dash 6. So this is how an electron get transferred from M dash to M. In this process you can see no ligand has changed its position, just oxidation number of M and M dash was changed, and therefore this process was called only electron transfer process. Various factors may affect the electron transfer process like CFAC, redox potential of metal complexes, and hard-soft acid-base interaction. For example, transfer of electron would be easier if Ma plus is cobalt 2 plus and Mb plus is chromium 3 plus and L dash is moderate in its strength. Then electron transfer process from cobalt 2 plus to chromium 3 plus would be easier, as by doing so a high spin D7 arrangement of cobalt ion converts to low spin D6 arrangement. This extra stability acts as a driving force for such a reaction of electron transfer process. Detailed discussion of the electron transfer process will be the module that will be presented later on. Now let's go towards the next kind of reaction, that is displacement or substitution reaction. In aqueous solution, ligand binds to metal ion not in a single step but in every successive step a ligand gets substituted against a water molecule. Such kind of reaction in which a ligand gets substituted at the place of a living group of metal complex is called displacement or substitution reaction. Generally, three kinds of substitution reactions are reported. They are dissociative, interchange and associative substitution reaction. Here we are giving a brief introduction of such reactions, detail of which will be discussed in later section. In a dissociative reaction mechanism, X breaks from ln mx and form an intermediate ln m and X. In this intermediate ln m, Y group gets substituted to form ln my. This kind of substitution reaction involves two-step process in which living group breaks first and then a ligand, that is attacking ligand, attacks to fill this vacant site in the subsequent step. Step 1 is a slow step and step 2 is a fast step, as in the step 2 Y is fulfilling the vacant position of the M, and here is the positive hole and negative cloud supply kind of interaction between the two. In the interchange mechanism, you can see here, before breaking of X, Y get attached from the same side of the metal where X was already attached, and then X was released from the system to form a new complex ln my. Interchange reaction is a single step process in which association of ligand doesn't increase coordination number of central metal atom or ion. Instead, an ion pair as a transition state used to form in between the reactant and product. So it's a single step process but is different from the associative reaction mechanism. To differentiate, let's learn about the associative mechanism. In this case, a ligand Y was attacked onto a substrate ln mx. Generally it used to attack from the rear end of the X, and a 180 degree angle is generally used to form between X, M and Y. And then ligand X breaks from the system to form Ln My molecule. Associative mechanism involves formation of an intermediate with increased coordination number of metal atom or ion, which follows a dissociation of a ligand X. During substitution reaction, electron count in reactant and product do not change. Even some complexes which are thermodynamically very stable undergoes substitution reaction. Complexes on which substitution reaction takes place very rapidly are called labile. Otherwise, complexes are called inert complexes. Detailed theory of lability and inertness in the complex is discussed in the next module. So, before completing this module, let's summarize. Every system, atom or molecule wants to be independent and self-sufficient, and therefore atoms and molecules react to form different complexes. Metal complexes undergo different kind of reactions like association or addition reaction, elimination reaction, insertion reaction, substitution reaction, etc. Principle of reactivity of metal complexes, which seems extremely stable, depends on various factors including keenness to form 18 electron system, steric strain, LFAC, redox potential, etc. So that's all about the module.